Hello, good afternoon, good evening, good morning, whatever time zone it is where you are while you're watching this video. I'm Dr. Mohamed Nezami. This is the third part in the series on the what we name is the post layout RF performance verification. Again, I'm an independent freelance RF circuit and microwave circuits designs. I do my own consulting. If you have any designs that you would like to outsource, please don't hesitate to reach me at this phone number here or via email in here. You could also contact me by using these mobile phone apps, WhatsApp and Telegram. Okay, so last time, in the last two videos, I would like to bring your attention to my YouTube channel. If you don't mind, if you could just go in and subscribe, I would appreciate that. But last time we have spoken regarding the verification and validation of the RF performance of PCB designs. And in this particular example, I'm taking as an example a KU band low noise block down converter. Okay, so you can go back and watch these two videos. Okay, there's a third video which started this whole where the system design of the LMB was carried out. You could also refer to that. The link is shown in these here. You could, if you click on the information here, you have my contact in here. This is the link for the original videotape that detailed the KU band system design. If you like to support this effort, please don't hesitate to do so. I would appreciate it and I would like to thank the individuals that already had done that. You could go to this link and make a donation if you like. Okay, so this video here is oh no, this is not what I wanted. Okay, this is the video that I was talking about. Okay, this design of KU band SATCOM. This one is about a year ago. Okay, so let's close. Well, let's stop this and well, we could close it even. And let's just go back just to refresh your mind. So we started about a year ago. I did a system design for a KU band LMB. You can refer back to this video that detailed the insights of this. In that design, I did two filters. One was for the local oscillator, and one was done for the front end filter. And this was done using the filter synthesis tool within the Keysight Genesis program. Okay, so this is an app that you give it the specification of the filter and comes out with the microstrip work. So in the previous two videos, what I did is I focused on basically trying to take the existing layout of this LMB and then trying to do a post layout verification using electromagnetic simulators. And in this case, it was a ADS and RF Pro from Keysight. Next videos, I will be doing the same thing except when using HFSS. So you can watch back the past two videos. That's what I covered in here. So the past video covered the bias network on the LNAs, basically the radial stub based. So today, what I'm going to do is I'm going to go back to this layout here Okay, and then I'm going to go further deeper into this. As you know, post layout verification, really what we're trying to do, we're trying to locate areas, key critical areas where we can go in and chop or dissect the board and bring it into EM simulators. This is Cadence right now. This is in Cadence. Okay. So what we're trying to do, we can take parts of this like I did last time. I took the hairpin filter on the front end and then took the yellow that was between the amplifier and mixer QFN packages and the times 4 multiplier. So today, after looking at inspecting this further, there are two traces, this trace and also this trace. Let me take out this here so it can be more clear. This is a microstrip trace that goes from this QFN to this passive and mimic device in here, okay, which is a switch. And there's another one here. And these, when you look at these, there are some warnings, concerns. One of them is basically the vicinity, the closeness vicinity of this to this, to this two pads for this capacitor here. And the other one is this one here, the closeness of this to the to this package, the ground copper pore, and for this packaged device here. Okay, so which is an inductor. This is DC RF choke. So what we're going to do is I'm going to go in and basically sweep the signal from the QFN, this pin here, okay, all the way to this pin, to the pad for this passive component here. And I'm going to do the same thing since this trace is also close by. I'm going to do the same thing for this one, okay? So let's go back to ADS, and I'm gonna, as you recall, what I did basically is we go to this and we export. I export basically the ODB++ on this, and it basically gives you the board that in a portable form that you can import into other packages, and that's what I did here. So I imported this board, and this is what we got here. Not this, I don't want this, but let's see, this is already this one here. So let's go to here, and what we have here is we're gonna look at these two traces in here. So I'm gonna highlight this and highlight this one as well. And I'm gonna go to the EM tool and cut these basically. So I'm gonna do this. So if I preview this, this is what it's gonna cut. It's right to the edge, so I don't want that. I want to extend it further than that. So let's preview this, and that's what it's gonna get. So it's gonna get part of the QFN ground bottom pad, which is good because that's a reference to this pin. And then on this side, it's gonna get just the pad on this side. Okay, it's going to get a little bit over here, but that's all right. So let's go ahead and cut this out. Okay, and that's what I got right now. So that's what we got. So we're going to take this. And of course, if you zoom in on this, it's complete. You can see that the vias are there. Okay, and the ground plane is there. Okay. So what we want to do is we're going to add ports to this and run the simulation and see what we get. What we're trying to do basically is look at the return loss and the insertion loss, see if there are any issues that has to do for the fact that this is so close to this. And the reason we want to do this is because you might get a suck out or a notch in the frequency response that is really not very far from the band of operation. So we want to make sure that that's not going to happen. So let's do this. So first we're going to get the ports. So we're going to put a port right here. And I'm going to put another port right here. Another one right here. Okay, another one right here, and now we're done. Trying to make sure the stack layer is fine. So this is wrong. So we're gonna fix that. The substrate is Rogers. So let's go this Rogers 4003. Okay. So we do this and yes it. Okay, so now we're all set. So we're gonna run the RF Pro, export it to RF Pro. Let's see what we get. Okay, so basically came in, you can go to the Z-axis exaggeration button here and inspect this and make sure that it's all fine. Okay, so we can go in and see where the ports are. Here's one pin. We can see that that is there. That's good. The other one, and then the fourth one. So we're all fine. Now, so if you go to the solidify this, you can see that this is the ground plane and this is the top PCB. Okay. All right. So let's do this. Gonna expand this, and let's make a reference plane first. The reference plane, we're gonna assign it to the bottom ground, and we're gonna take all these pins and grab them and put them into the simulator. Gonna go into options and just run it from, don't want to run it to that much, just to 6 gigahertz, that's fine, from 1 gigahertz. Okay, now this is a KU band LMB, but this part, these two traces in here, really, they have to do with the part that is carrying the local oscillator signal from the phase lock loop module, okay? And that basically, if you look at that, that's basically running at the S-band, 3 gigahertz. So we go 3 gigahertz, phase lock loop, lock to an overnight crystal, and then we multiply by 4 to get to the local oscillator value that we want, which is somewhere between 9 and 11 gigahertz. Okay, so we're gonna run this down in the SC band, sort of like up to 6 gigahertz, and see what we get. All right. Let's see what else here. Go to the options, the simulator, momentum microwave. Okay, so we're all fine. I think so. Let's just run it, and hopefully this doesn't take very long. Let me see if it does. I'm gonna pause the recording and then come back when it's done. All right, so while it's running, let me go back to the layout here and locate another area that I want that I have a concern. And this time around, I'm going to put this layer here, the 7th layer on, and I'm going to hide the top one. And what I'm going to do is, this is a trace here. Just make sure that see this trace here. Basically, this is, if you look at the layers, this is on 7th layer. On top of that is a ground layer, and on the bottom is a ground layer. So this is really a strip line layer. And this signal in here is one of the signals, which is basically takes the amplified OCXO 10 megahertz reference. It takes it from the top, brings it down to this 7th layer, sandwiched between 2 grounds. And this here, if you calculate at a width of 8 mils, it turns out to be that you're going to get this width here, which is somewhere on the order of between 8 to 10 mils, and then takes it back to this module, the phase lock loop module. So I want to see, this is a critical trace here. It involves a transition that you go down basically from from top, you go from top down to this layer here to the 7th layer. So this is strip line, which is critical. We want to sweep that as well. Let's go back here and see if this is done. This is still running. Okay, so simulation has ended. Took about 3 minutes. So let's see what we got here. Go results. And basically what we have, if you want to look at the geometry again, so we have pin 1, so pin 1 is here to 2, 1 to 2 is this trace here, and then 3 to 4 is this trace here. Okay, so let's see what the S parameter sweep. So we've got 1 to 2. Okay, and our return loss is 1 to 1. So let's magnify this. So already looking good. So it doesn't look like there's any issues. Okay, so the loss is very minimal in here. So, and the return loss is better than 15, minus 15 dB all across from 1 to 2. So we look at, let's look at the other trace, 3 to 4. Okay, which is also not bad. So 3, 3 is this. And again, this is good. So it looks like this trace is good. All right. So that shows we're okay. So really these traces here that we have some concern about this trace here and the fact that it's so close to these vias, these don't seem to impact anything at the frequencies that we are interested in, which is below 4 gigahertz. Okay, so I take this off. All right, so let's go next is we're going to go to this, like I said, so let's look at the this here. This is a strip line that takes the OCXO signal, the amplified and filtered signal or shaped signal, into the phase lock loop, one of them, okay? So let's go ahead and look at that. And to do that, I'm gonna close this. So we're done with that, save it, yes. And I'm gonna close this again. Okay, so let's go to the ODB this time. So basically, this is the trace that I'm going to look at. This is the trace that I'm going to be looking at. Okay, so what I'm going to do is let's go ahead and chop. Now, the transition that I have is this one here. This is a transition from top to layer 7 to go into this net here, which is a strip line. So you could, what I could do is I could look at the effect of this transition alone, okay? Or I could look at the whole line. So let's do both. First thing I'm going to do, so I'm going to go to the EM in here, EM tools, and cookie cut this and preview this. So now this tool here in the software, the ADS Keysight software, it's a little bit different than HFSS. I think HFSS handles this much better, but we'll see that in the next videos. So let's preview this. So we're gonna go, this is good. So we're gonna capture all of this. So let's cut this out only. So cut that. Oh, okay, so cut it. Okay, so this is what we've got. And let's just make sure that we are fine on this. So let's look at the 3D. Okay, so now that's another thing. So we need to assign. Okay, so this is the stack layer is all fine. So we did assign that. So let's assign it while we're doing this. Yeah, let's, okay, so assign this. Okay, so if we go 3, no, I don't want this. No, not this. Okay, this is the one I want. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the right one. Okay. Okay, so this is the cut piece. So what we want to do is we want to look in here. This is the transition where the signal goes from here all the way to the 7th layer and come back again on this side. So if we can come in here and restart offset, let's just zoom in on this. And I'm just gonna, well, okay, so let's go to 7th layer in here. This is 7th layer. So this is the trace we're interested in, okay? So that's this guy here. Okay, so he did come through. So if we put those put the top on, this is basically what we have. So we have these, and let's put the drill on. So we have all the, okay, so what we're gonna do is we're gonna put a port on this, a port on this side, on the top layer, and another port on the other side. Of course, we don't have anything to do with layer 7 or to the strip line layer because we basically go in from top down to that one, and then we go back in there. So we don't need to put any excitements on the 7th layer. Okay, so let's save this. Before we save it, let's go ahead and run out of Pro. Okay, so we're here. So if you look at this, now this is basically an exaggerated liftoff of this, and you can see that what we have is we have an input on this side, which is this input here that goes in, and there's a via. This is the via where the signal is coming in. It goes all the way in until the to layer 7, which is this layer here. You can see that it's going to that one. And then, of course, you have the trace on layer 7 going all the way across to the other side. Now, one of the issues of why we're concerned with this, of course, now this happens to be running in megahertz. So this is for the reference for the 10 megahertz, is the fact that even though we're coming to the 7th layer in here, this is 7th layer, but the via continues downward. So you have an open stop in here. And I have some videos on that using HFSS analysis on designing transitions between in a stack layer. But this via here that will go from 7 to the bottom to the ground, and you can see it's clear from the ground in here. So it goes to the bottom of the board right here. This one is basically going to be at some frequency. It will act, because it's open, it will act like a short, and it will create a notch in the frequency response, okay? So let's see, if we look into this and we come in here, look at the conductors. So we're going to take all of them off right now, set them invisible, and let's go to the 7th one and set that as being visible. Okay, so basically that's what we have here, is that what we try, this is the trace that we're trying to analyze, okay? So basically we're going to run this and see what the frequency response is done. Now, because this will take some time, this is a sizable copper area, and it will take a sizable amount of time to run. So let me save this for a little bit later, but let me go back to this here. And let's say that I want to look just basically on a on just this, on the transition itself. I want to analyze the transition. So I could do is just go here, and then I'm going to cut that. Okay, so basically, okay, let's just set that up. Okay, so but let's go again and cut this further, because we really don't need to be that much. We just need a little bit so that we can study the this. So let's go again and chop this out too. Okay, so this is good. So if you look at this now, let's look at it in 3D domain. And this is basically what we got. This is just the transition. Okay, so all it is just the pad. This is a pad, okay, with a via that we want to study. And the this goes to the seventh layer, which, let's see why I'm not seeing it here. Okay, because we don't have all of them. Okay, so we can analyze this separately. Okay, so layer 7. Okay, layer 7. Okay, so there's layer 7 in here. So what we want to do is to actually look at the here it is. There's a trace. Okay, so we want to look. No, see this. Okay, it's between layer 7. And so what we will do is let's turn all of these off right now. Let's turn 7 again here. Oops, that's the dielectric. So we're gonna put 7. Okay, here it is. Okay, so what we're going to do is let's do this. I'm gonna put an input port on this. So we're gonna go to 7. That's a signal 7. Okay, so we're gonna go, I'm gonna put a port on this. Okay, and then I'm gonna put all of them on, and then the other port, I'm gonna put it on top at the input place. So we're gonna go here and put an input on this one here. And now what I'm gonna do is I wanna go in and take this also to RF Pro. And the reason we want to do this is because most of there are any issues, big issues, they will be basically on the they will show up in the transition. Okay, so what we're doing here, we're going to study the impact to go in from the transition from the top layer, the microstrip, to the strip layer. The strip layer in here, that's this trace here. So we could also cut it right to this point here if you want. In fact, we may want to go do that as well. So let me go back. As you can see that the trace is too long, so let's just chop right here. Okay, so we're gonna do just basically this like this. Okay. Okay, that way we can get more narrow down the impact of just the transition rather than having an additional shape. Okay, so we're gonna again put take them off. Okay, and put 7 on. Signal 7. Take out this. So I'm gonna put the excitation on this is on this layer, okay? And the other one should stay in, so we didn't do anything to that one. So, okay, the other input is right here. So now let's go again, take this into RF Pro. Okay, so now we're much better. You can see that this is much better. Okay, so let's run this. And what we want to do first is create a, take the inputs into the EM simulator. Well, let's make a reference plane. The reference, I'm going to still reference the bottom, the first ground layer, but it'll take care of itself because the vias interconnect all the ground sublayers. All the sublayers that are ground basically are hardwired via using vias. So I'm going to take that to here. Okay, there are some issues with this, but that's fine. Okay, so this is what we do, and this is going to take time to run it. So I'm going to cut this video here, and let's continue on the next video. So again, what we're doing basically is we're still trying to basically analyze the effect, so locate some critical areas of the board and that we have laid out that we want to send to fab. And before we lose a lot of money on PCB fabbing and PCB assembly, we want to see if we can catch any issues that might cause deterioration of performance. So we want to do post layout verification. Okay. So again, thank you for watching this video. Please, like I said before, if you happen to be involved with any RF designs that you would want to source, I operate out of Jerash, Jordan. I go back and forth to the US, so I could visit clients that are in the US or in Europe. My rate is very reasonable because of the operating outside the Western Hemisphere, which is much costlier than this part of the world. So go ahead and contact me. Basically, my service charge is very reasonable, and I work with you from specifications all the way to production. Basically, walking you through and working with your team. I will design things for you, system level, convert them down to schematics, do the PCB layout, and then provide you with fab and assembly design files and everything. Okay, well, until next time, I thank you very much. Thank you and have a great day, everyone. Thank you.